Okay, so thanks Pierre-Louis for joining us, for giving a talk at your own place here. So he has chosen the title and he will explain us, you all know it, the high dimensions, what Pierre-Louis wants to tell us.
Okay, thanks a lot. It's really a great pleasure to have this, the last day of the Bardos festival. Or should I say Bardos, to be more precise. The last day of his festival here in Collège de France. I'm not responsible for the choice of pictures, right? Mine was not necessary, but you know, in the end, everything was done by Kaiser Norbert. But I think it was really thank you, Norbert, for this idea, because it made a lot of sense. In fact, I think that Claude spent quite a lot of time, lots of Fridays in Collège de France, especially some time ago when my father was there. Okay, we all love Claude. That's a fact. Why? Good question. I have no idea. No, sorry. Well, I think the main reason is that, well, he is what one should say that he is, I don't know how to say it in English, un honnête homme. Okay, so that's a 17th century expression, that meant someone who was cultured, who is humble, and who is also very pleasant. Pleasant meant, of course, pleasant in high society, typically at court. And of course, in Claude's case, that was pleasant at the court of King Jacques-Louis. And probably in English one could translate that by decent man. I think it's the closest translation I can figure. I will talk a little bit about his maths later on. But first I want you to realize that Claude has a superpower. He's the only person who can speak quite distinctly with a cigarette, unlit cigarette, dangling from the corner of his mouth, which is an achievement. You should try, but it's... And he did that for quite a long time. I met Claude a long time ago, professionally. Maybe I saw him as a kid, but I don't remember. I didn't care about all those mathematicians that were going through my home. Mathematically, it might be around 78, 79. Okay, for the young people, I'm talking about 1978, 79, not 1878, 79. So that's a long time. And of course, I have lots of anecdotes. You know, if you spend some time with Claude, you will end up having lots of strange anecdotes. There is no way you can escape that. Okay, so a few. It's not clear I will be able to say much math, huh? But I think it might be more pleasant. That's a story I already told in the vid I made for a meeting that was organized in Texas, in Austin, for Claude. I couldn't attend. I sent a vid, and I told a few stories, and I will add one more. We were in a meeting together in New Brunswick at Rutgers University, and Basilis Guidas had offered us to share an apartment. But the first, unfortunately, last time I shared an apartment with Claude. So we shared an apartment, which was Guidas' apartment, with Claude and Henri Berestiki. So you can imagine the two opposites. Henri, who is quite fussy, and Claude, who is not that fussy. The last day, well, during that meeting, we had this conversation which shows that Claude had some form of... he's a naive guy, huh, from time to time. And he told me, I don't understand. Whenever I take a plane, there is no one sitting close to me. I just ask him, open your bag. Open his bag, and there was papers, dirty laundry, everything. So of course, I think that people were afraid to sit near to him because I don't know what they could imagine. But anyway, on the very last day, everybody at the end of the day was fine. We were quite early. We decided to go inside on Main Street to get a coffee. We get there with a car, and suddenly Claude gets out of the car and starts running. I forgot my passport. Okay. Then he runs, disappears. We had no clue where he was going, probably to the apartment. So we decided to go to a cafe and wait there. And we waited and waited and waited. Maybe after a very, very long time, we see Claude running, shouting and so on, running in the street and saying, I have my passport. It was in my bag. And then we get out of the cafe. Unfortunately, the car had been towed away. Since then, okay. Anyway, another meeting, a few anecdotes with Claude, which will illustrate his super ability to solve problems. We were in Cargés, in Corsica, a town in between Ajaccio and Porto, Ajaccio et Porto in French. It's a beautiful place, like the mountain falling in the sea, quite typical of Corsica. And Claude, at the end of lunch, decided to bring us coffees. We were a large table and so on. So that was very kind. He's a kind man. And he went and put all the, I don't know, 6, 7, 8 coffees on a big tray. And then he had to move from one room to the other. And the problem is that the tray was too big for the door. Okay? No way. No way. Problem. He solved it. Another anecdote is that during that week, we decided, we were really stupid, we decided with Joel Smaller and again Henri Berestiki to go and run one morning. Strange idea. So 8:30, July, Corsican sun, a road which was essentially going up in the mountain because the only other road is the one with all the cars near the sea. And well, we went. I had stopped playing rugby not so long ago, so I was still at that time somewhat in shape. Smaller was always running, so he immediately ran out like a rabbit. I never saw him again. And so I tried my best. And then Claude started. It was an interesting, very interesting. So I have to confess that I felt a little bit like, oh, hee. But well, I'll tell you the rest later on. So very slow pace, very slow. And so I was running. Of course, Henri, after 200 or 300 meters, decided it was too tough and went back to take a coffee. And I ran and ran. After a few kilometers, I was completely out of breath, completely exhausted. Smaller had disappeared. And so I decided to stop at one point. So enjoying the view in the mountains, seeing the sea and everything. That was absolutely beautiful. I really had difficulties to catch my breath. And suddenly, whom do I see? Exactly at the same rhythm as the beginning, Claude. Now, so very slow, but very, very, very efficient. So I felt a little bit, I was jealous. I was willing to make fun of him at the beginning, and then there he was. I was completely out of breath, and it looked okay. Well, I succeeded in to convince him that he was out of breath and that he should rest and we should go back. Fortunately, he accepted it. So lots of good memories, but as I say, that's. There are many human qualities which are even much more important than anything we can do in math or whatever. And that's, I think, the main reason why we, well, I don't even know anyone who disliked him. That's almost suspicious. Mathematically, as I said, I've known him for many, long time. What you don't know, Claude, is that I was not trained as a PD guy or an analyst. I was trained as a probabilist. And but then I was very much interested in the connections between diffusion processes and, of course, PDEs, so I had to learn PDEs and so on. I was very much interested in a paper by Struck and Varden, which was about exit problems for diffusion processes. One of the best problems, which is not the most well-known compared to the martingale problems and so on. That's another story. And so I wanted to see a little bit what exists on PDEs when you can have degeneracy or when the noise goes to zero. And one of the first papers, because I learned PDEs reading books, and one of the first papers in PDEs that I read was by Claude. It's not a well-known paper. It's on a singular perturbation for essentially minus epsilon Laplacian plus a first-order term. But it was simple, very clean, very well done. And of course, the issue is about boundary conditions and where to impose directly boundary conditions and so on. And there was a discrepancy between what people do in probability theory and in PDEs. But that was the first paper I read. Longer, much more, well, I don't know, maybe 2 or 3 decades afterwards, there are 2 papers that I want to mention. One could analyze many more articles, and François just did about this, the hydrodynamic limit for the linearized Boltzmann equation. There are 2 that I want to mention. One, which for me is really a landmark for specialists of conservation laws. That's the famous paper by Bardos, Leroux, and Nedelec on scalar conservation laws with directly boundary conditions. This was a very clean paper that was giving the right answer to that question, which is much more complex than it seems. How to impose for hyperbolic equations, scalar equations, nonlinear scalar equations, how to impose some form of boundary conditions. And of course, later on, there was, in fact, I'm not sure about and this was a paper that really was an inspiration for us in various studies about junction problems, about scalar conservation laws that we did afterwards. Of course, there is one paper, and I already mentioned it during François On's birthday in Zurich. I just simply consider their joint paper with François and Dave Livermore on the various asymptotic regimes of Boltzmann equation. I simply consider it as one of the best papers I've read. This is really a beautiful paper. And I did learn a lot through this paper. It clarified a lot of things I knew more or less, but it was so clear. Well, so those are just a few examples that show that although we did not always work on related problems, of course, I didn't want to have anything to do with controllability and so on. And you did a great job there, especially in connecting with the more linear PD people. I'm thinking of Lebeau and others, and that was, I think, very useful, but this is not a subject I ever really thought hard about. And anyway, so you were indeed very influential. Time to say a few words. You see this strange title, Remarks on High Dimensions. And maybe I'll say a few words. Some of the stuff is pretty old, and some of the stuff is pretty recent, since it's, in fact, even a work in progress. What is old is the things I developed some time ago because of Minfield games. And what is more recent is to systematically understand what happens when you add randomness in all those issues and noise and so on. And there are various motivations for that. The latest being trying to understand a little bit what goes wrong with neural nets and how one might be able to improve what's taking place. Okay, so 3 short parts. One which is going to be about points and differential equations. Second, which is going to be about continuous functions, differential calculus, and equations. And third, well, A2, that's strange, ABC, more about transformations and, in some sense, operators. And this is really work, the last part is really work in progress. I don't really know. So if I write here, it's okay. My brother is there, it's not okay. No, okay, so I shouldn't write, okay. Hey. So basically what we want is to have what we are interested in are things that take place in Rd to the n, like n particles, each particle being in Rd, or in e to the n, where e is a nice metric space. Okay, so by nice, what do I mean? Well, it's a Polish space, a separable complete metric. So D will be the metric for on E. On Rd to the n, I'm going to simplify the presentation by saying that the metric I'm going to use is 1 over n sum from 1 to n. xi now lies in Rd. Pick up any norm you want. They're all equivalent. That's irrelevant. So that's in some sense the one norm on the product space. Okay. In fact, the best metric one should use is a Prokhorov metric. But it takes 5 minutes to explain what it is, and it's a little bit complicated. It's more classical in probability theory than in analysis. The main idea being the Prokhorov metric, and this metric is that if you take a finite number of points, or if you take, so this is a norm, the metric is of course associated with that norm. If you take a finite number or a small compared to n number of xi, it modifies very little the end result. So in some sense you can neglect a finite number of points. They don't play much role, okay? And the Prokhorov metric measures this in a much more precise way. But that's exactly the idea. So I'm going to use symmetry. So I'm going to use the relationship. Actually, yeah, that's certainly true. The relationship, which is to say that x sigma is if x1 and xn are the components, that's the components of x sigma. So, of course, we may look at the quotient space, Rd to the n, by the perturbation, by this group of transformation, and because essentially, if we have a problem where all the particles are exchangeable, or whatever the word, or identical, whatever the word we want to use, then x or the permutation of its components are just exactly the same point. Of course, when you do that, you have to equip it when you're doing metric spaces, and you are looking at the distance. The associated distance is going to be the inf over all sigma of 1 over n, sum of I of xi minus y of sigma I. Okay. And what I realized a long time ago, and I was not the first to realize this, is that, of course, one way to think about such equivalence classes is to introduce the empirical measure, which is, of course, in the set of probabilities on E, It's simpler to write. And I will insist on one because this is the one distance, okay? I will not be paying attention to the to situations where A is not bounded or not compact and so on. But one has to be a little bit careful because whenever, let's say, E is RD, there are always tightness issues. You don't want to lose any mass at infinity. I will just ignore the technicality here. Okay, so clearly, the distance on the quotient space is the Wasserstein distance between, let me call this mx, and my. Totally classical. Which means that there is an isometrical embedding of this quotient space in the space of probabilities. The range of this embedding is precisely the set of all empirical measures, which in the end essentially grow. Well, it's not really an increasing sequence, but that's irrelevant, but it essentially grows to be something which is dense in P1. So in the end, you approximate any measure, okay? Fine, so that's a simple, very simple observation. I want to make two more remarks, which will be useful for what follows, is that x plus y, no. Okay, what does that mean? This means that, of course, when you take x in RD to the n, y in RD to the n, x plus y makes perfect sense. But in terms of equivalence class, it doesn't work, because it might be different permutation on x and y, unless y is a function of x. Okay? But if we look at x plus h of a certain b of xi, so I should write it more component-wise, possibly I will ignore that. You have a symmetric function of all the other components, and let me denote by Bn. Well, at least, so do not worry about that part. At least this makes perfect sense, okay? And of course, this is like the earlier discretization of an ODE. Huh? So really, what I'm interested in, so this is yes. Because whenever you make a permutation, well, you make the same permutation, of course, in those guys. So, which means that if we look at x dot equal b of x, and possibly this, but I don't want to keep it, b of xi, then it's a yes in terms of saying that we can represent it by empirical measures, and those empirical measures, as n goes to infinity, we have compactness. All those guys, as n goes to infinity, goes to something, right? Here they go to something, and what you get is dm over dt plus divergence of b, and typically, if you keep all the mess, equals 0. So what I want to do is not so much reproving things that can be proven in thousands of ways, but to look at the pictures to see how the notions are being organized, in order to see, given a specific problem, what is the difficulty, if any. Okay? So typical difficulty in such a thing would be as singularities. Implicitly, in everything I'm going to say, there are no singularities. And I will mention from time to time what happens when you have no singularities. Of course, I just mentioned stochastic DEs. Okay? So let me change the notations and let me write dx dt. Well, if you have, and you have this idea that, globally the evolution has some kind of symmetry by exchange symmetries. So one option is to have an alpha, and I don't want to say from what it depends, but typically it's xi, another guy. And it should be the same, for instance, driving random term, let's call it a Bardos motion, except that in order to have something which is meaningful, one needs to do it because we are essentially following trajectories, so it should be the Stratanovich integral. In which case, what you have here is a stochastic PDE. It's exactly the same. Yes, correct. So all this, if everything is smooth, requires essentially no work. It's automatic. Note, however, so I'm going to change the color, is that if I were to add another term, depending always on the same guys, with a Bardos motion which is now not the same, independent Bardos motions, everything breaks down. Because you don't stay anymore, you know, whenever, if you do a permutation of the I and x, you're going to change the Bardos motion. They are not the same. Okay, so there is a real issue here on which I will come back later on. So in some sense, we are no more in that quotient space as soon as we have independent random noise. Okay, that's puzzling because I'm going to now mention now the PD interpretation. Before I do that, so you see it's really a catalog of observations. Okay, so before I do that, I have to recall a very old observation I made, again because of Minifield games, which is to say, let's take now continuous function on the quotient space. Let me call it RD to the n, and let me assume that we have a function phi n, which has some kind of uniform modulus of continuity with respect to the distance I just mentioned. So let me call it d1 of x and y. Okay. And let me assume that phi n is symmetric. Use this representation. You can really think that phi n is a function of m and x on the empirical measures, which has a uniform modulus of continuity in W1, because now we are looking at those functions of measures, of probability measures. Okay? Are equicontinuous. Okay? And they are not defined on the whole of P1, but they are defined on a set which becomes a full set. So it's the same. So it's essentially as Collier-Yarzela theorem, and you know that this converges uniformly whenever m and x converge to m. This converges to some function phi of m, up to subsequences, of course. So in other words, continuous function with the right modulus of continuity, with the Prokov distance, with the one distance, are the same as continuous functions on the space of probability measures, period. Okay. There is almost no proof. That's a proof. Okay? It implies, trivially, the Finetti-Hewitt-Savage theorem. Two lines. Okay? Linear continuous linear forms. Okay. The converse is also true, but it's much more complicated. One really needs to work a little bit. In fact, the proof, and in fact, I've seen that some people are now using this proof, is to use, and something that I call the monomials on the space of probability measures and so on. So it's completely equivalent, but I find it much easier to describe the Finetti-Hewitt-Savage theorem in that manner. Okay, fine. That's old. some old stuff is that, of course, instead of having continuity, you can have Lipschitz, and you get some notion of Lipschitz, which is, of course, with the P1 distance. You can have C1, C2, you have differential calculus. So clearly, differential calculus n go to infinity creates a differential calculus on the space of priority measure. Okay? Some authors are calling it the Lyon's calculus. I hate that. Because I think it's so natural. It's just you play a usual calculus in Rn, and you just lift it on the space of priority measures, that's it. And, but what pleases me is to see that people working in statistics, like Mark Hoffman and so on, it happens that some convergence result in statistics depend on the regularity of the functional you're interested in, and how to measure the regularity, well, you need some differential calculus, and that's a differential calculus. No big deal. It's also equivalent to the differential calculus on yet another interpretation, which is an L1 of omega, where omega is not an open, regular bounded open set in RD, but a probability space. Because there is yet another interpretation, which is what we call in mental games the so-called Hilbert interpretation. Of course, L1 is not really an Hilbert, one should say a Banner interpretation, which is to say, well, there is still another equivalent way to see that, is to say I'm going to look at all random variables such that x equal xi with probability 1 over n. So now I'm embedding those guys in a much bigger space. So I add it to the n, contracting it through the symmetries to that quotient space, becoming a compact set. And now I'm completely unfolding everything, and I'm embedding in the set of integrable random variable. Okay? So which means that differential calculus in Rn means, what it means when you embed everything in random variables, which is to say that phi of m is now defined on all random variables, provided, of course, the law of x is m. Well, if you do that, then you have the usual differential calculus. So you see it's the flat differential calculus in a Banner space L1, and it's what you obtain as n goes to infinity. And of course, you can pass to the limit in various PDEs. So let's go back to the PDE here. Let me forget the alpha, and let me concentrate on the DWI. So clearly, those are the differential equations, stochastic differential equations, which are lurking behind, here in that simple case, which are lurking behind a parabolic equation, which is now dun over dt, which is going to be bn gradient un, and bn is going to be bn is going to be let me say a little b. Bn is going to be something like a bn of xi, and a symmetric function of all of the other guys. Which means that in the sense I'm mentioning here, this converges to some b of x, I, and m, if the empirical measure goes to m. Then, if I ignore the common noise which cannot disappear in the end because it's pushing everything, if I forget the alpha term, what do I have? And let me take sigma to simplify to be okay, sigma to simplify to be identity, do I want to do that? No. Minus half of a trace of sigma, and I'm sorry, there is a minus here, sigma transpose d2un. And it's also sigma n with exactly the same dependence. Sigma n is some sigma of xi. Okay, so this goes to some sigma of x and m. I said before, we cannot use general recipes to pass through the limit in that guy when you have noises. But if I average out, taking the expectation, then I have an equation like that. And what I just said, indeed tells you that if you look at the dual equation, in order to have, it goes to what you expect, dm over dt, plus divergence of b of x and m, minus the divergence of, okay. I'm trying to do things which are okay. So that's, of course, if sigma is 0, you have a Vlasov-like equation. If sigma is not 0, you may have a rather complex equation. Again, if everything is smooth, everything is justified and can be shown very, very simply using this, this machinery, but I'm not claiming this is true. It's just to understand how it gets organized. So what's going on? Here, we cannot really pass to the limit in the empirical measures, at least using the general approach. And here, it's trivial. Of course, there is an expected value in between, an averaging taking place. So let's look a little bit more precisely in what's happening. First of all, is that dealing with a problem like that, you may say, well, I look at the dual equation and I want to prove propagation of chaos. Propagation of chaos, which in terms tells you that the limit probabilities and probability is concentrated on solutions of that equation. Okay, so you can do that. What about this, this theorem or this observation? Well, the uniform convergence, that's how I call this, implies propagation of chaos. Trivially. 2 lines. So that's a very simple way to deal with those things. And the converse is true if you have a deterministic equation. Okay? Because usually what one says is that propagation of chaos is deterministic, but not stochastic. The reason, so typically in propagation of chaos, you have to start off with a symmetric probability, okay? A symmetric probability density. Here, when we look at the empirical measures, we have one configuration. There is no symmetry between x1 and xn. It's a Dirac mass at that point. Okay, so what's the point? Well, the idea is quite simple. I can show it here. Well, this I can erase. I won't be needing it anymore. And yeah, the idea is quite simple. So we are really interested in one point delta x with x1, xn. And so I'm going to randomize it with the counting measure on the set of permutation. And this is what I'm going to use as an initial condition for the dual equation, the Fokker-Planck equation. Now I have got something which is symmetric. In terms of empirical measure, they are the same, because all those points yield the same empirical measure. That's because the evolution is deterministic and perfectly preserve the symmetry. Okay? So when you do that, well, you may try, let's try to use propagation of chaos. Well, what you need is to understand whether this n probability is indeed originally propagation of chaos. The answer is no, but almost. Okay? So under that, you have asymptotic propagation of chaos, which is good enough. Asymptotic chaos, because I'm not propagating anything. And the reason, with a bunch, some of Dirac masses thinking you have independent stuff, it's not clear. In fact, if this is something like Mn, and you compute Mn2 minus 2 particles, marginal with 2 particles, with that, in total variations, this is bounded by, if I remember correctly, 2 divided by n minus 1. That's an exercise. You just apply the definition and you do it. Which means that, and the same is true for the case density probability, and taking the case, and then you have something, a constant that depends on k divided by n. It's surprising. But in fact, you apply Mn2 to a test functions, you compute explicitly. So that's, it seems like a miracle. No, it's not a miracle. So in principle, you can use propagation of chaos strategy to prove the convergence of the empirical measure for a given configuration. Except that in order to do so, you need to be able to prove propagation of chaos with very bad initial conditions. So if you have smooth data, that's okay. So everything is equivalent to everything, as usual. But if you are dealing with singularities, and of course my interest lies in various experience I had recently with such stochastic particles interacting with quite singular potentials, then you see that the proof that goes by the analysis of empirical measures and gives propagation of chaos is very robust. Basically, you just have to worry a little bit about the singularities, but that's it's quite simple. Because typically when you have singularities, and if you're able to prove results on propagation of chaos, you're assuming quite a lot of regularity on the, let's say, initial distribution. So that's, but the converse, I don't know. That's in the deterministic part. In the stochastic part, it's worse, because the stochastic part, PDEs give you only some information, which is average one. Okay? So if I'm now interested in stochastic particles, so now I have an empirical measure that, of course, depends also on omega. It's now a stochastic probability measure. And you see that it's going to work. You can make proofs if everything is smooth. You can make proofs directly. No big deal. Writing down the Ito's equation associated to this stochastic empirical measure. And what you see is that the martingale part of this formula goes to 0. And it goes to 0 even if the noise, this guy here, the sigma, doesn't go to 0. If sigma goes to 0, you are asymptotically deterministic, it's the same story. But if it stays there, okay, there is no, why should it become deterministic? And it becomes deterministic. This goes almost surely in omega to the m, which is the same m as before. Okay, so not only in expectation it goes to the m, but in fact almost surely it goes to the m. And the reason is indeed that the stochastic part of the evolution goes to 0. And it goes to 0 because you have Wi's, which are IID, and you have the law of large numbers. Okay? So you have two different phenomena which are both of, in nature, are somewhat reminiscent of the law of large number. That's the limit as n goes to infinity, the limit of empirical measure. And on top of that, even if you have quite a little bit of noise, but they are independent, you have the law of large numbers. How can you combine both? So that's, let me make this remark, and I'll check with the Kaiser with how much time I have, but I want to make this remark. So I will ask after. So beyond symmetry. So I confess that I've been playing with all kinds of crazy algebraic ideas, which is to say when we take e to the n and this space e to the n, so as n goes to infinity we have sequences of points. Let's assume that e is bounded. It's not a question of bounds. And clearly we want to impose a metric where whenever we have a finite or number of points, they don't count. So essentially, these are the same sequence if you erase a finite number of points, or a number that grows slowly to infinity compared to n if you take subsets of type n. So you take the lim sup of the A1 norm of samples of size n. So in the end, you get a metric space. The quotient operation is to say that all sequences whose distance is 0 with this lim sup distance are the same. So typically, a sequence that converges to 0 is 0. Because essentially, you need only you have essentially a finite number of things which are relevant, and you can ignore them. So one gets a metric space. Unfortunately, it's not complete. So one would need to complete it. At that point, I said, okay, forget it. Huh? But I wonder, because I think it's a little bit the difficulty. In some sense, you're measuring size of objects by C0 means, and it's very reminiscent of the type of difficulties one has, topological difficulties one has with Besicovitch spaces, almost periodic spaces. So I don't know. I think I'm too old to develop, and it's too abstract to develop that. But it's curious. I don't expect compactness. There is no way one can invent something which is compact. Compactness comes from the symmetry, reducing the complexity with respect to the symmetry. But let's go back, beyond symmetry. So here is something that will explain what I meant by, and in fact, we started looking about that because of neural nets. Well, 1 minute about neural nets. Take a layer of neurons. Typically, the way they are numbered is completely equivalent. So you have hidden in the architecture of the network, layer by layer, you have hidden an invariance by permutation of the architecture. Now, many reward cost functions, and all the operations preserve all those transformations. That's part C. All those transformations preserve the symmetry, but symmetry is a catastrophe when you want to minimize something, because suppose that you have a symmetric function to minimize of n variables. Generically, all the components of the minimum are going to be different. Okay, x1 is different from x2, etc., etc. Which means that if you have a minimum, you have a huge number of minimum, all the permutations. Okay, so we try to do things using standard neural nets algorithms and just inserting noise in various spaces to break the symmetries, and the speed up was pretty good. But this is only the beginning of the story, and as I said, this is work in progress. So what do we have here? What we have is an fn function of 2 variables, x and y. So the x is as before, and I want to say that the fn converges to a function. So there are 2 variables. It's going to be a functions over probabilities, which are on if x, let's say, lies in Rd to the n, and y will lie, and we'll see in something that I will call I don't know, g to the n. And pi is going to be a probability on Rd cross g. Fine. Now, the function I'm really interested in, so that this is a setting. So in order to have that, this just means that we have a uniform, we just have such a condition up to a subsequence. This means that we have this uniform continuity with respect to D1 in x and y. And now let's look at the following quantity, which is Fn of x. And as for y, I'm going to put some yn here, where yn is y1 up to yn. And those are RAD with values in G. Okay? So what you have is a mixture of invariants by permutation. If there is no y, you would have a function which is indeed invariant by permutations, perturbed by independent noises. Okay? Double variations. And this goes indeed, goes to a function f bar of m, which is related to this function f by a trivial formula. It's, okay, it's an elementary proof, requires a few lines of computation, and well, one has to make the proof. I don't want to make the proof. But now you understand what I was saying, is that namely the stochastic empirical measures, whether you have independent noise, yield a deterministic equation in the end, and that's exactly the same phenomenon. As an example, here is an example, a few examples, sum of fi of xi, where the fi are RID in the space of continuous function. So you take randomly, according to some law, it may not be completely the whole space of continuous function. You sample, you take random functions fi, or you take randomly function fi, and you look at this as a function of x1, xn. Or you could have some of, I don't know, okay, so maybe let me take this one. Yi like weights in a neural net. Yi you add. Here you can add, because I'm not saying I'm living in the quotient space. Okay? I'm living in RD to the n. You add YYD, take the plus function, because that's a natural operation, and you have an operation on the layer. All these can be, in the end, gives functions, have the same type of convergence towards function of the space of priority measures. So that's what one can do. It's symmetry plus randomness. In the end, that works. Okay, there is a third part, but I think it might be a good idea to stop there. The thing is really to say, okay, now I have this x. Now I have a transformation from e to the n to some other space T of x. And if so that's the identification I want to make, and the identification I want to make on operator is if P sigma is a permutation matrix, what I want to take is this. So that's the identifications. So if points are up to a permutation, what are transformation up to the permutations of the points? Okay. So of course there are going to be operators on the space of priority measures, and that's just the beginning. There is much more to be said, but it's high time to stop. Claude, it has been fun, not this talk, but it has been fun to know you for so many years. I certainly hope that we'll have many more years to have more fun without necessarily sharing an apartment with you. And thank you for everything, Claude.